Hello everyone, welcome to Computer Science. This is the part 3 video of our topic computer codes. Our subject is computer fundamentals, and in this video we will be discussing about two types of computer code, self-complementing code and gray code. The previous video we have discussed about the ASCII code, EBCD IC code, Unicode, and in the part 2 video we have discussed about gray code, not gray code, BCD, binary coded decimal, then XS3 code, then weighted codes. Okay, so today we are going to discuss about the self-complementing and gray code. What is a self-complementing code? If a code is constructed such that when we replace a 1 by 0 and a 0 by 1 in the 4-bit code representation of a digit d, we obtain the code for 9 minus d, that is 9's complement. That is called self-complementing code. Okay, the concept is uh, a simpler one. That is when we interchange the zeros and ones in the 4-bit representation of a digit d. Consider a digit, suppose it is 2. Okay, the 4-bit representation of 2 is 0010. Okay, so the 4-bit representation of a digit d, this is digit d. Then, when we interchange the zeros and ones in this 4-bit representation of a digit d, so I'm going to interchange the zeros and ones. So, 1 is placed in the place of 0. We write 1, and in the place of 1, I'm writing 0. Here, 1. 0010 changed to 1101. And if we obtain the code for 9 minus d, the 9's complement is 9 minus d. Our d is 2. So 9 minus d means 9 minus 2, that is 7, right? 7. If the code for 7 is same as this, then this code is said to be a self-complementing code. Okay. When we interchange the zeros and ones in the 4-bit representation of a digit d, if we obtain the code for 9 minus d, that is the 9th complement, then this code is called a self-complementing code. For example, our 2421 code is self-complementing. A weighted code is said to be self-complementing if the sum of its weight is equal to 9. Okay. So now this point, a weighted code is said to be self-complementing if the sum of its weights are equal to 9. 2 plus 4 plus 2 plus 1 equal to 9. So this 2421 code is self-complementing. And consider our 8421 code, our commonly known as BCD code, right? Our BCD code is not self-complementing. Consider its weights 8421. 8 plus 4 plus 2 plus 1. It's not equal to 9, right? So this code is not self-complementing. A self-complementing code need not be weighted. Okay, not this self-complementing is not the case only for complementing. I mean, for this weighted codes, this unweighted codes also can be self-complementing. For example, our XS3 code. We have discussed about this XS3 code in our previous video. This is an unweighted code and it is derived from the BCD 8421 by adding 3, right? 0011. This is the binary equivalent of 3 to all code groups. 8421 code, XS3 code. XS3 code is derived from 8421 code by adding this 0011 to each 4-bit groups of this 8421 code. And this XS3 code is a self-complementing code. 2421 code is a self-complementing code, but our 8421 code is not self-complementing. Generally, a weighted code is said to be self-complementing if it's a sum of its weights are equal to 9. And what is a self-complementing code? For a digit d, consider the 4-bit representation when we interchange the zeros and ones, and if we are getting the code equal to 9 minus d, that code is known as self-complementing code. Consider this example. Here, this is our BCD code. This blue color code is BCD, and we are adding 3 0011 to each digit, and we will get an excess tree code equivalent to each decimal digit. Okay, so this is excess tree code, and this code is self complementing. This blue color is 8421 code, and this is not self complementing. Let's check. Consider this number 0000 decimal 40. Okay, when we interchange the zeros by 1, we will get 1111, right? And if that 1111 equal to what? 9 minus D, right? 9 minus 0. Okay, 9. Code for 9 is 1001, which is not same as 1111. So we can easily say that 8421 is not a self complementing code. But here, in case of excess tree code, the code for code for 0 is 0011, right? 0011 is the excess tree code for 0. Then when we interchange the zeros and ones, we will get 1100. And 9 minus 0, that is 9. The code for 9 is same, 1100. Consider the next number 0100. When we interchange zeros and ones, we get 1011, and it should be equal to 9 minus 1. 9 minus 1 is 8. Consider the code for 8, 1011. This is same. Next number 0110. When we interchange zeros and ones, we will get 10001. Our number is 3, right? Our number is 3. So 9 minus 3, 6. The code for 6 is also 1001. This is the structure of the self-complementing code. We consider the 4-bit representation, and we have interchanged the zeros and ones, and we get the code equal to 9 minus D, or we get the code of 9's complement. This is the concept. Okay, let's move on to the next topic, that is cyclic code or reflected code or gray code. All of these are same. In a cyclic code, each code group does not differ from its neighbor in more than 1 bit. Okay. So let's consider this term Hamming distance. Hamming distance between two equal lengths binary sequence of zeros and ones is the number of positions in which they differ. Hamming distance between 0110 and 1010. Hamming distance between two equal length binary sequence. So this binary sequence is of 4 length, and this is also length is 4. So these are two equal length binary sequence. Then the Hamming distance is the number of positions in which they differ. So consider the first position. Here it is 0, here it is 1. So this is a difference. Our distance is 1. Consider this number. Here, second position, here it is 1, here it is 0. So our distance is, another position is added, right? So our distance is 2. Then a third position, here it is 1, here also it is 1. Fourth position, here it is 0, here also it is 0. So our Hamming distance is 2. The Hamming distance between two equal length binary sequence of zeros and ones is the number of positions in which they differ. In cyclic code, Hamming distance between two successive code group is unity. So this is the definition of a cyclic code or gray code. Here, the Hamming distance between two successive code group is unity, that is 1. Okay, what is the Hamming distance? It is the number of positions in which two equal length code groups differ. So this Hamming distance should be 1. Gray code is not weighted. That means it does not depend on positional value of a digit. This is a cyclic variable code. That means every transition from one value to the next value involves only 1 bit change. We have already discussed that this Hamming distance between two successive code group is 1. So this is also a cyclic code. Every transition from one value to the next value involves only a one bit change. Suppose the code for 1 is gray code for this 1 is 0001, then the gray code for 2 will be 0010, something like that. So there will be only a single bit change. The Hamming distance bit will be 1 for each adjacent code groups. The next value involves the transition from one value to the next value involves only one bit change. For 1 to 2, there will be only a single bit change. For 2 to 3, there will be only a single bit change. So on. Gray code, also known as reflected binary code, because the first n by 2 values compare with those last n by 2 value, but in reverse order. Okay, let's check all these points in the coming sessions. So we have discussed the definition of gray code. What is a gray code? The major characteristics of gray code is each code group does not differ from its neighbor in more than one bit. Here the Hamming distance will be 1. Gray code is a cyclic variable code. Gray code is also known as reflected code because the first n by 2 values compare with those last n by 2 values, but in the reverse order. Next, how to convert a binary number into a gray code. We have discussed how to convert a BCD into XS3 code by adding 0011, right? Likewise, how to convert a binary number into a gray code. In the gray code, this is the steps for conversion. The MSB will always be the same as the first bit of the given binary number. We will be given a binary number. We have to convert that binary number into a gray code. For that, the first bit, the MSB of the binary number and the MSB of the gray code will be same. To find out the second bit of the, so we have find the second bit, sorry, first bit, right? The first bit will be same as the MSB of our binary number. Then to find the second bit of the gray code, perform the XOR operation of the first and second bit of the binary number. It means that if both the bits are different, the result will be 1, else the result will be 0. In order to get the third bit of the gray code, we need to perform the exclusive OR of the second and third bit of the binary number, and so on. Let's consider an example. This is our binary number 1011. We have to convert this number into a gray code. So the first bit will be same as that of gray code. Okay. So I have written the one over here. This one is copied to here. Next, to get the second bit of gray code, the step is to perform XOR operation of first and second bit of binary code, right? In order to perform the second bit of the gray code, in order to find or in order to get the second bit of gray code, perform the XOR of first and second bit of binary number. So we have to perform the XOR operation of first and second bit of binary number. XOR of 1 and 0. If both bits are different, the result will be 1. Else the result will be 0. The characteristics of XOR operation is this. When both bits are different, our result will be 1. When both bits are same, the result will be 0. Here both bits are different. Our result will be 1. That 1 is placed here. To get the third bit, we have to perform XOR operation of second and third bit of binary. XOR of 0 and 1, we get 1. Then to get fourth bit, we have to perform the XOR of next two bits, 1 and 1. So there is no difference. Our value will be 0. 1011 binary is converted to gray and our code is 1110. Let's consider another example. Our number is 1010. We have to convert 1010 into gray code. First, the MSB is transferred here. So our gray code's first bit is 1. Then to get the second bit, we have to perform the XOR of first and second bit of binary. XOR of 1 and 0 will get 1, right? The two bits are different. Our result will be 1. 1. To get the third bit, we have to find the XOR of second and third bit. XOR of 0 and 1 will get 1 because the bits are different. Okay. Last bit, we have to perform the third and fourth XOR. Here also the bits are different. Our XOR value will be 1. So 1010 binary is equivalent to 1111 in gray code. This is the conversion. Next, okay, uh, another conversion. Next, gray to binary code conversion. So we have converted a binary code into gray. Now the reverse process. We can convert a gray code into a binary code. The steps. The first bit of the binary number is similar to the MSB of the gray code. So first step is same. In order to perform the second bit of the gray code, perform the XOR of first bit of gray and second bit of binary. I will explain with an example. Our code is 1010. Okay. Then the first bit of our binary code is same as the first bit of gray code. This one is transferred to here. Then, in order to get the second bit, we have to find the XOR of first bit of binary code and second bit of gray code. In the previous example, we have performed an XOR like this. But here we have to perform an XOR like this. Okay, these two bits, the first bit of our binary and the second bit of gray code, and these bits are different, our XOR will be a 1. Then to get the third bit, we have to perform XOR of second bit of binary and third bit of gray. The result 1 1, so the result is 0. To get the fourth bit, we have to perform the fourth bit of gray and third bit of binary. Result is 0. 1010 is equal to 1100 in binary. Next example, 1101. 1101 is our gray code, and this 1 is transferred here. And to get the second bit of binary, we have to perform XOR of second bit of gray and first bit of binary. Here the digits are 1 and 1, so our result will be 0. To get the third bit, we have to perform XOR of second bit of binary and third bit of gray. Digits are 0 0, our result will be 0. Then to get the fourth bit, we have to perform XOR of fourth bit of gray and the third bit of binary. The digits are 0 and 1. Our result will be 1. 1101 gray code is equivalent to 1001 in binary. Hope the conversion is clear. Next, we have discussed that we have said that our gray code is a reflected code, right? This is the characteristics of a reflected code. The first half, that is n by 2. The n by 2 compares to the last n by 2 in reverse order. So n by 2 means here we have 16 digits. By 2 means 8. First 8. Consider the first 8, 0 to 7. Consider this 3 bits. Okay. The last 7th position is 100. And for 8, our value is 100. Okay. Here 6 is 101. 9 also is 101. 5 is 111. 10 also 111. The only difference is that the fourth bit, that means the MSB is, for the first half MSB is 0, the next half MSB is 1. Then all that other bits are same in reverse order, right? This line is like a mirror. Above and below digits are same in their position. Okay. This is the reflected property of our gray code, but for binary this is not the same. Consider the binary number here. For 7 our number is 111, but for 8 it is 000. Here 110, but here 001. So this is not the same, and the gray code is a reflected gray code. But here this for in case of binary, this is the reverse, or I mean when we interchange this 1 by 0, these are the complements. Okay, here for 7 it is 111, for 8 is we interchange all 1 by zeros. For 6 it is 110. When we interchange this ones and zeros, we will get 001. That is for 9001. Okay, when we interchange here, we get 010. That is same for 10, 010. Okay, this is the nature, reflector nature of gray and binary codes. Okay, hope the concept is clear. So we have discussed what is self-complementing code and what is a gray code, the reflector gray, the definition of gray code, how to convert a binary to gray and gray to binary, then the reflector nature of gray and binary code. Hope the concept is clear. Thank you.